I'm relativist, the stand-in a way for Einstein in all of this, a bit like Salviati, who in Galileo's dialogue of two world systems was a factotum for Galileo himself. I'm Kritikus, a kind of amalgam of Einstein's nemeses, a bit of Friedrich Adler, a bit of Philipp Lenard, one of Einstein's most ardent critics and later a Nazi whom we'll meet in a further part of the course. People like me have often expressed their criticism of relativity in journals, but rarely have one of you relativists actually shown up to respond. Maybe it's out of a feeling of weakness, maybe it's arrogance, maybe it's laziness, maybe it's a toxic brew of all three. Or maybe it's that the critic has shown by what he says that he didn't know what he was talking about. But right now, I will not leave until you've answered all of my questions. I am not, like some of my colleagues, so steeped in the great honor of my guild that I'm unable to approach you as a mere mortal, a human. And unlike some of your critics, who approach this as if they were prosecutors accusing you of intellectual theft and other dishonorable acts, I am going to address the problems of relativity on their merits. Here's an example. If you consider a Galilean frame, that is to say a frame of reference where nothing's being accelerated, then if you have a clock, call it U1, that's stationary, and another clock goes by, call it U2, U2 seems to be running slow compared to U1. But grave problems arise if one considers the following. Now imagine that you've got this U1 clock fixed here, and U2 goes by at some velocity, so it seems to be running slow compared to U1. And then it turns and comes back, it still seems to be running slow compared to U1. Do you agree with that? I agree absolutely. It saddened me, in fact, that so many of the people, even those who agree with relativity, have tried to avoid this conclusion. Time, the relativity of time, is probably the most radical part of my theory, and some people who like the mathematics of it seem to try to avoid this fact. But now comes the snag for you relativists. If instead of focusing on U1 and having U2 go out and come back, where U2 is running slow, we went with U2, then it looks like U1 has gone out and comes back. But then U1 is running slow compared to U2, and U2 is running slow compared to U1. That can't be. It leads to an inescapable contradiction. Your entire reasoning is based on a false assumption. It is not legitimate. The theory of relativity, special relativity, is valid for Galilean systems, systems that are not accelerated. But when you follow a clock that goes out and turns around and comes back, it is accelerated. And so there's nothing wrong with using relativity properly. The system K, fixed on clock U1, is a Galilean system. The system that goes out, turns around and comes back is accelerated and is not Galilean. Consequently, no contradiction can be deduced from the fact that U2, after it goes out and comes back, is running slow compared to the stay-at-home clock U1. I see you have diffused my criticism, but all this leaves me more convicted than convinced. Now that's probably Einstein's sly aside, meaning that Friedrich Adler was rotting in jail during this, more convicted, if one could say that, than convinced. But my objection could be resurrected from the dead if one uses your theory of general relativity, because general relativity says one can take the point of view of any frame, including ones that have acceleration. So I could have a frame nailed to U2 as it goes out and comes back. What do you say to that? It is certainly correct that we can make a system that follows K prime out and back. But that does not mean that k and k prime are equivalent for the process under consideration. Let's look at this in more detail. First, let's take the simple case of k. In reference frame k, we have a nice Galilean frame, nothing's accelerating, and clock 1, U1, stands still. Clock 2 takes a rocket, accelerates out, goes at a constant speed v. At a certain point it turns around, the rocket pushes it back, and then the rocket slows it down when it gets back to U1, and sure as shooting, U2 is slow compared to U1. But what does this look like if we take the point of view of clock 2, if we take the k prime frame? Then we'll describe the situation rather differently. We look at U2 and we say it's kept in place, say by firing its retro rockets, as a gravitational field is turned on, and U1 falls away, accelerates out, and then the gravitational field turns off and it just floats along at v, and then the gravitational field turns on, pulling it back towards U2, and it goes back, and then eventually we turn the field on again to slow it down and stop it when it arrives back here. Now, an object falling in a gravitational field, as U1 does, and then when we turn the gravitational field around, it's still falling in a gravitational field. And then when we turn another gravitational field on to stop it, U1 feels no forces. It's a free-floating object, as if you were a worker falling off a roof and you looked at your hammer and saw it floating next to you, as if there were no gravitational field. So U1, in this thought experiment, really does simply sit as if nothing was happening, even though from the point of view of U2, a gravitational field has turned on, accelerated it, turned off, let it float, turned on, turned it around, turned off, let it float, and then turned on and stopped it back next to U2. So that's a very different way of understanding this from the point of view of clock number 2. So we illustrate this, and we see U2, from the point of view of reference frame k, U2 is accelerated out by rocket, and the rocket pushes it back then to U1. From the point of view of U2, the gravitational field is turned on, the U1 clock floats away, the gravitational field is reversed, and it heads back. Here's the conclusion that should satisfy you completely. In the U1 frame, where it just stays still, and U2 goes out and comes back, boosted out by a rocket, turned around by a rocket, stopped by a rocket, U2 ends up as having elapsed less time than its stay-at-home twin U1. The question is, what does this look like from the point of view of U2, and does it give us the same result, namely that U2 has fallen behind U1? It does. Here's why. From the point of view of U2, they start out together, gravitational fields turned on, but it affects both equally because they're right next to each other. U1 falls away, gravitational field's reversed, and it comes back. Special relativity tells us that U1 is actually running a bit slow compared to U2, but there's a bigger effect. And the bigger effect is that at the turnaround point, U1 is high up in the gravitational field compared to U2. And we know what happens to clocks that are high up in a general relativity situation. What happens is clocks up high in a gravitational field run fast. That's what happened in Jefferson Laboratory when Pound and Rebka experimented. They found that the clocks at the top of that 74-foot tower ran fast compared to the ground. It's why GPS satellites run fast a couple of hundred miles above us compared to their twins on the ground. So at the turnaround point, when I turn on that gravitational field to make U1 come back to U2, its clock ran fast. Fast enough to overcome the slowing down by special relativity. Fast enough to exactly give us the same result as we had from the point of view of U1. Namely, U1 runs fast compared to U2, according to general relativity. And it does so in a way that is saying the same thing as U2 running slow compared to U1. So both frames of reference, K and K prime, give us the same result. Clock U1 compared to clock U2 says U2 is running slow. From the K prime frame, it says U1 is running fast compared to U2. That's the same thing. And so we have no paradox, and it's entirely resolved by thinking about the way clocks behave in a gravitational field. But isn't this gravitational field merely fictitious? It seems by moving around your coordinate system this way or that, you say you generate gravitational fields. But gravitational fields can only be generated by real masses, not by the choice of a coordinate system which makes them disappear or appear. How could an arbitrary choice of a coordinate system lead to a different rate for the clock? It seems completely a confusion of the real and the fictitious. You can't really say it's fictitious or it isn't fictitious. You see, we know this even from kinetic energy. If I have a bullet and I ran alongside it at the same speed as the bullet, I could just take it out of the ground. If it was sitting next to my shoulder, it would just stay there and fall down. So the energy of the bullet depends on the frame of reference. If you have a piece of space junk and you were to come at a very fast speed in a rocket and hit it, it could knock a hole in your spaceship. So frame of reference can influence real effects. So it is in general relativity. If you fall with the worker and the hammer, you see them stationary, as if there was no gravitational field at all. It's the same thing. Choosing your frame of reference can make a difference. After your last comments, I have to concede that the clock paradox doesn't seem enough to disable the theory of relativity. In fact, it may be that the theory of relativity is internally consistent. But even if it's true that the theory of relativity is internally consistent, I still don't see why internal consistency is enough to make us adopt this theory of relativity with all of its complicated mathematical notions and ideas. We have to accept the complications that relativity theory leads to for several reasons. First, any thinking person would recognize that there's something wrong with the idea of absolute motion. Already at the time of Galileo, we knew that there was no way of saying we are absolutely at rest or traveling at a constant speed. So I'm just generalizing that idea. Second, the equivalence principle captures something deep. If you fall with a gravitational field, in a gravitational field in free fall, it's as if the gravitational field didn't exist. Or if you accelerate at the same rate as the gravitational field pulls you down, there's nothing in that acceleration that could tell you that it wasn't a real gravitational field. These ideas are built into the theory of relativity. Finally, without some principles, without some basic starting points, we are faced with an infinite number of alternative theories of gravity. Embarras de richesse, the too large number of possible theories can only be restricted by a principle which narrows us down to the road forward. And finally, there's the precise measurement of the motion of Mercury around the sun, which general relativity predicts. For all these reasons, the equivalence principle, the elimination of the idea of absolute rest, a restriction on the possible theories that narrows things down to give us very few theories and ways forward, and the concrete measurement of Mercury. For all these reasons, Kritikus, you should come around. It's worth accepting the mathematical complications of relativity. I have to admit that after this discussion, it seems a lot harder to disprove the theory of relativity than I might have thought. Still, out of curiosity, what is the status of the sick man of physics, the ether? the sick man's had a rather fluctuating fate in theoretical physics. Back in the day, in the middle of the 19th century, it was thought to be a kind of real fluid, like a gas, only even rarer. Lorentz fixed that and made it a rigid, all-pervading substance. Special relativity showed Lorentz's idea of an ether to be superfluous. It was killed off. But now with general relativity, it does seem that by studying the gravitational potential, the quantity that leads to the gravitational field itself, we can understand that there actually is a kind of property of space. In work that I've done, I've even showed that you could have waves in the gravitational field, as if they were waves in a new kind of ether, an ether that goes beyond anything imagined in the 19th century. But don't think that it's a substance like a fluid or a gas. It's a state of the gravitational potential, the quantities, the mathematical quantities from which we can calculate how strong the gravitational field is in different places and its effects. Did I convince Kritikus or his descendants? I rather doubt it. You can argue with them all day long, and for decades to come, these same criticisms come up over and over again, despite being refuted by ever new experiments and technologies. The stubborn critic persists. Einstein's play may not be Shakespeare, but it does register the seriousness with which he took his critics, and provoked by the objections of people like Leonard on the enemy side and his erstwhile friend Friedrich Adler on the other, Einstein was pushed to come up with new and clear explanations for things like the twin paradox as seen from general relativity. So we look at this play, at the battle between criticus and relativist, as a kind of time capsule, capturing Einstein still very much ready to do battle with his critics as World War I drew to a close.